So we're going to just look at the simplest possible flow, uniform flow. So for uniform flow, here's what this looks like. U equals U infinity, V equals 0. Here's your X, here's your Y. And let's figure out what potential function and psi would look like for that flow at least. So we know that for the potential flow, d phi dx is equal to U, which in this case is equal to U infinity. So we have the equation that d phi dx is equal to U infinity, and d phi dy, which is equal to V, is equal to 0, which means that phi is only a function of x, right? There's no y dependence of phi. So phi is only a function of x. So we can go ahead and integrate this partial differential equation, first order. D phi is equal to U infinity times dx, and we can take the integral of both sides of that, and we get phi is equal to U infinity times x plus some constant of integration. If we can set phi equals to 0 at some point. Let's set phi equals 0 at x equals 0. That's just the simplest thing to do. And so you end up with a final function, phi equals U infinity x. So that is the entire phi function for the uniform flow field. So very, very simple. If you take a y derivative of that, of course, you get 0. So d phi dy is equal to 0 because derivative of a constant times x with respect to y is 0. And of course, d phi dx, as we hoped, comes out to be U infinity. So that gives us back the flow field that we wanted. If you look at the stream function, doing the same type of thing, you find that you have d psi dy is equal to U infinity. So d psi dy is equal to U infinity, and negative d psi dx is equal to 0. So that's your U term, that's your Y term. So that means psi is only a function of Y. And of course, that's easily integratable with the same technique. I won't bother to reproduce that very simple integral. It comes out to be U infinity Y. So this psi function increases and decreases only in Y. The phi function increases and decreases only in the direction of X. So if I were to put a grid here and show you lines of constant psi and lines of constant phi. So constant psi would be 0 at y equals 0, if this is y and this is x. And then it increases as y goes up. Of course, it has a constant value. It just equals U infinity times y here. So whatever this is, that's what it's doing at a constant way. These lines should be equally spaced. Those are lines of constant psi. And lines of constant phi, well, it's kind of the same. It's 0 at x equals 0. And then it goes up linearly as x increases. So it's going to go like this. Those are lines of constant phi. These are constant phi. So you see that they are perpendicular to each other. And they are always perpendicular to each other. So psi and phi, constant, I should say constant, psi and phi lines are always orthogonal, which means perpendicular. I think I spelled it wrong, but anyway, orthogonal. And the direction of flow is tangent to the streamlines. That is, the streamlines are the lines of constant psi, and they're perpendicular and orthogonal, obviously, to potential lines. So if you're looking at this and you know these are lines of constant phi, the flow is going to travel with the lines of constant psi, lines of constant psi with the streamlines. Flow travels with the streamlines, travels perpendicular to these lines of constant phi. So that's that. If we wanted to look at a slightly more interesting case, we could try to draw the lines of streamlines of for a situation. So I'll draw a very beautiful airfoil here. Here's my airfoil. And I'm going to draw streamlines first. So the streamlines are going to come straight in. They're going to hit the airfoil, come straight out the back. that's going to be a stagnation point. And then what are the streamlines going to do? Well, they're going to have equal spacing, but as they go over the top, they're going to be slightly closer together, because slightly closer together streamlines means slightly faster flow. That's going to be a steeper gradient. So they're equal out here in theory. They get a little tighter as they go over that little hump, and they speed up a little bit, and then of course they eventually don't do that anymore. And they just end up being the same all the way across. And going under, they more or less don't do much of anything. Just like that. So that might be your streamlines for this flow. And notice they go right along the surface. So this streamline is actually traveling right along here. Constant streamline there, bifurcating around this airfoil. Slightly tighter spacing here. That means slightly faster flow, because the y, if you want, is the u, right? So d psi dy is the magnitude of u. So the tighter those are, the steeper the gradient is, because these are lines of constant psi, equal differences between them. So that's how you can see where flow is fast and slow. You look for tighter streamlines, gives you faster flow. More widely spaced streamlines gives you less fast flow. So d psi du is that, and d psi dy is greater if streamlines are closer together. So that's true. And then if I were going to draw the potential lines, they start out here just doing nothing, just straight up and down as the flow uniformly comes in. Now remember, they're always perpendicular to streamlines. So it's a little easier to draw the streamlines, because you kind of know the streamlines are going to do this, flow over the wing. It's not really clear what the potential lines are going to do. They're just going to stay perpendicular to the streamline, so they're going to come off at an angle here and then go up. I kind of screwed that up. They shouldn't change their spacing that much. At any rate, there we go. Kind of going like this now. And these are going to be pretty much just coming off the bottom, pretty straight, maybe a little bit of curve there. So that's your kind of a gross, pretty bad map of what streamlines and potential lines would be doing. Orthogonal to each other, going around this airfoil. But you can kind of see why people like these. The streamlines in particular really give you a sense for where the flow is going, and that's why streamlines, I think, continue to be popular for people to use and think about. It's a very nice way to visualize flow, even if these days it's not really much of an advantage in terms of computation, because we have really good ways to compute complex flows.